Change of variable, dummy variable. Okay, so let's begin with a concept that often surprises students when they first encounter it. Welcome to our discussion on change of variable, or what we call a dummy variable. Now, when you're working with definite integrals, and you've been practicing those, I hope, it's very common to get fixated on which variable we use inside the integral. You might be thinking, should I use x, t, or maybe u? It seems important, right? But here's a fundamental idea that's easy to miss. The variable inside the integral, like x, t, or u, is actually just a placeholder. Think of it like an empty box. It holds a value as we calculate the area under the curve, but the name of the box doesn't change the amount inside. In mathematical terms, we call this placeholder a dummy variable. It's a bit of a quirky name, but it's accurate. What we'll explore in this section is why the specific letter we choose for this variable doesn't actually change the final numerical answer we get when we evaluate a definite integral. We'll see that the definite integral gives us a specific number, and that number doesn't care what letter we use to get there. In the next few slides, we'll look at examples and analogies to really solidify this concept, and also address some common mistakes students make. Understanding the concept. The title here is Understanding the Concept, and we begin with what we're calling property P0. This property essentially defines what we've been discussing. It states that if you have a continuous function, and remember, a continuous function is just one you can draw without lifting your pen, over a closed interval from a to b, the value of the definite integral will not change, no matter what letter you use for the variable of integration. Let me break that down. We're saying that the integral of f of x with respect to x, evaluated from a to b, is exactly equal to the integral of f of t with respect to t, evaluated from a to b, which is also equal to the integral of f of u with respect to u, evaluated from a to b. Now, let's look at the mathematical expression. We have the integral symbol, then f of x, then dx, indicating integration with respect to x, and the limits of integration are a to b. This is exactly the same as writing the integral symbol, f of t, dt, and the limits a to b. And again, the same holds true if we use u instead of x or t. So why is this true? Well, a definite integral, like the one we've been looking at, the integral of f of x dx from a to b, doesn't give you a function as an answer. It gives you a number. That number represents the signed area under the curve of f, x, between the points x equals a and x equals b. Because the result is a number, the letter we use to represent the variable being integrated, whether it's x, t, or u, is actually irrelevant. The x simply tells us what we're integrating, but once we apply the limits a and b, the variable effectively disappears. We're just calculating a value, and the name of the variable doesn't affect that value. Okay, so let's move on to slide 2, where we'll formally state and understand this idea of a dummy variable. Think of it like this. If you're calculating the area of a rectangle, you use length times width. It doesn't matter if you call the length L, or W, or Z. The area will be the same as long as you use the correct numerical values for the dimensions. The variable name is just a label. We'll solidify this concept with an example on the next slide, but this slide lays the groundwork for understanding why we can freely change the variable of integration in a definite integral without changing the result. Remember, we're building towards avoiding common mistakes, which we'll cover later, so it's important to grasp this fundamental idea now. Real-world analogy. Okay, so we've established that the variable we use inside a definite integral, whether it's x, t, or u, doesn't actually change the value of the integral. It's just a placeholder. To help make this even clearer, let's think about something completely different, baking a cake. Imagine a recipe instruction says, add 200 grams of sugar. Now, in this simple instruction, the word sugar is acting like our variable. It represents something we're adding, but the specific name isn't crucial. If we were to replace sugar with sweetener, or even just call it ingredient X, the instruction would still mean the same thing, add 200 grams of that substance. We're still adding the same amount, right? That's exactly what's happening with definite integrals. The name of the ingredient, or in our case, the variable like x, t, or u, doesn't change the actual quantity, which is the value of the integral, the area under the curve. It's the limits of integration, the a and b in integral from a to b, that determine the quantity, not the variable we use to represent the function being integrated. We'll solidify this with a step-by-step example on the next slide, where we'll actually calculate the same integral using different variables to prove this point. But this analogy should give you a good intuitive understanding of why the variable is just a dummy variable. Step-by-step example. Okay, let's solidify our understanding of dummy variables with a concrete example. This slide demonstrates that the variable we use doesn't actually change the value of a definite integral, just as we discussed. We're going to evaluate the integral of the function f of x, which is x squared, from x equals 0 to x equals 2. But we'll do it twice, once using x as our variable, and then again using t. This will clearly show you that the answer remains the same. Step 1. Using the variable x. Here, we simply write out the integral as it normally appears, the integral from 0 to 2 of x squared dx. Remember, dx just tells us we're integrating with our respect to x. Now, we apply the power rule of integration. The integral of x squared is x cubed divided by 3. So, we have x cubed over 3, evaluated from 0 to 2. The square brackets indicate that we'll be substituting the upper and lower limits of integration. Substituting the limits means we calculate the value of the antiderivative at the upper limit, x equals 2, and subtract the value of the antiderivative at the lower limit, x equals 0. So we have 2 cubed over 3 minus 0 cubed over 3. 2 cubed is 8, so that's 8 thirds minus 0 thirds, which equals 8 thirds. Therefore, I sub 1, which represents the integral using x, is equal to 8 thirds. Step 2. Using the variable t. Now let's do the exact same calculation, but this time, instead of x, we'll use t as our variable of integration. So our integral becomes the integral from 0 to 2 of t squared dt. Notice that the limits of integration, 0 and 2, haven't changed. That's crucial. Again, applying the power rule, the integral of t squared is t cubed over 3. So, we have t cubed over 3, evaluated from 0 to 2. Substituting the limits, we get 2 cubed over 3 minus 0 cubed over 3. This is exactly the same calculation as before, just with t instead of x. 2 cubed is 8, so we have 8 thirds minus 0 thirds, which equals 8 thirds. Therefore, I sub 2, which represents the integral using t, is also equal to 8 thirds. Step 3. Comparison. Finally, let's compare our results. We found that I sub 1, the integral with x, is equal to 8 thirds, and I sub 2, the integral with t, is also equal to 8 thirds. Therefore, we can confidently state that the integral from 0 to 2 of x squared dx is equal to the integral from 0 to 2 of t squared dt. This clearly demonstrates that the choice of the variable of integration, whether it's x, t, u, or any other letter, doesn't affect the final numerical value of the definite integral. This is a really important concept to grasp, as it will become useful when we encounter more complex integration techniques and also helps avoid common mistakes, which we'll cover in the next slide. Common mistakes to avoid. Okay, let's move on to slide 5, where we discuss some common mistakes students make when dealing with dummy variables. This is important to solidify your understanding before we move on to more complex integration techniques, as highlighted in the next slide. #1. Confusing the variable with the limit. Alright, so a really common mistake I see students make is accidentally using the same letter for the variable inside the integral and one of the limits of integration. Let me explain. Imagine you're trying to write the definite integral. A lot of students will write something that looks like this: integral from a to x of f of x dx. Now, let's break that down. We're saying integral from a to x of f of x with respect to x. While you might see this sometimes, it's generally considered bad practice and can even be technically incorrect. Why? Because it creates ambiguity. The x is trying to play two roles at once. It's both the upper limit of integration and the variable we're integrating with respect to. It's like asking one actor to play two different characters in the same scene. It gets confusing. The correct way to write this would be integral from a to x of f of t dt. Notice how we've replaced the second x with t. Now, t is only the variable of integration, and x remains solely as the upper limit. This makes everything much clearer and avoids any mathematical confusion. Remember, we established earlier that the name of the variable doesn't matter for a definite integral, so switching to t doesn't change the value. #2. Thinking the variable affects the result now, let's address another frequent misunderstanding. Some students, especially when they're first learning this, think that if you change the variable from, say, x to t, you also need to change the limits of integration. That's not true when we're simply changing the dummy variable. Remember, we've already shown with examples that integral of f of x dx is equal to integral of f of t dt, as long as the limits of integration, a and b, stay the same. The only time you do need to adjust the limits is when you're performing a technique called integration by substitution. In substitution, you're actually transforming the variable using a function. For example, you might say, let u equal some function of x, and then you would need to change the limits to reflect that transformation. But in the case of just changing the dummy variable, simply replacing x with t, the limits remain exactly the same. This is because the function f itself hasn't changed. We're still integrating the same function over the same interval, we've just given the variable a different name. So, to recap, don't change the limits when you're just switching the dummy variable. Only change them during integration by substitution. Key takeaways. First point, dummy variable. The variable we use inside the integral, whether it's x, t, u, or anything else, is called a dummy variable. The reason is simple. Its name doesn't change the final answer. We've seen this in action with our examples, haven't we? It's just a placeholder that allows us to represent the area under the curve. Next, numerical result. Remember, a definite integral doesn't give us a function as an answer. It gives us a number. That number represents the signed area under the curve between our limits of integration. Because it's a number, the symbol we use to get to that number is unimportant. It's like calculating the area of a rectangle. Whether you call the length L or W, the area remains the same if the numerical values are consistent. Now, let's look at property P0. This is just a formal way of stating what we've been discussing. It says that the integral of a function f of x from a to b is equal to the integral of the same function f of t. Also from a to b, so, mathematically, it's written as integral from a to b of f of x with respect to x is equal to the integral from a to b of f of t with respect to t. The key here is that the limits of integration, a and b, and the function f remain unchanged. Finally, a notation tip. This is a practical piece of advice. If your upper or lower limit of integration is expressed in terms of x, meaning it contains x, it's best practice to use a different variable, like t or u, as your dummy variable inside the integral. This avoids any potential confusion. We touched on this in the common mistakes slide, where we saw that writing something like integral from a to x of f of x with respect to x can be ambiguous. Using a dummy variable like t keeps things clear and mathematically sound. Okay, let's recap what we've learned about the change of variable, or dummy variable, in definite integrals. This is the final slide, so we're tying everything together. So that's it. Understanding the concept of the dummy variable is fundamental to mastering definite integrals. It simplifies things and helps you avoid common errors. Remember, the goal is to find the numerical value of the area, and the name of the variable doesn't affect that outcome.